Unit 3, Lesson 1. This lesson will align with 12.4 and 12.5 in your textbooks. The one standard in this lesson: give an informal argument for the formulas for the circumference of a circle, area of a circle, volume of a cylinder, pyramid, and cone. Use dissection arguments, Cavallari's principle, and informal limit arguments. A few formulas for us to go through. We've gone through these formulas previously, but it's always good to go through them again. First, the circumference of a circle. The circumference is equal to 2 times pi times the radius. The area of a circle, the area is equal to pi times the radius squared. The volume of a cylinder, the volume is equal to pi times the radius squared times the height. Volume of a pyramid, the volume is equal to 1/3 times the base times the height. If you notice, this base is a capital B. That base is referring to the area of the whole base, whether that be the area of a triangle or the area of a square. And the last one, the volume of a cone, the volume is equal to 1/3 times pi times the radius squared times h. The standard for this lesson says we need to provide an argument for where some of these formulas arise from. We're going to go through the circumference of a circle and try to grasp an understanding of why the circumference for a circle is c is equal to 2 times pi times the radius. All right, so we know that pi is involved whenever we're talking about the circumference or the area. Imagine we have this circle with a diameter of 1 unit. If that's the case, then the circumference of the circle is equal to pi. Okay, that is the relation between the radius or the diameter of a circle and the circumference. So a diameter of 1 unit, we know the circumference is going to be pi. We also know that all circles are similar. If we look at these two circles, we know they're going to be similar. We can create a few different ratios. The circumference of the second circle, C2, compared to the circumference of this first circle, C1, this ratio is going to be equal to the diameter of this circle compared to the diameter of this first circle. Looking over here, understanding that we know all circles are similar, thus we can create this proportion over here. We will also be able to fill in some of this information. We just discussed, if we look at the first circle, this has a diameter of 1. Thus, we know the circumference must be equal to pi. If we take this a step further, we know c sub 2, the circumference of the second circle, over pi must be equal to 2r over 1. Now, if we want to get the circumference of the second circle isolated by itself, multiply both sides by pi, and thus we will be left with c sub 2 is equal to 2 times pi times the radius. All I did was rearrange these terms. Thus, going back over this, since we know all circles are similar, we just created a circle that has a radius r, and we know the whole diameter is 2 times the radius. That's where this 2r comes from. Go through the proportion, solve it, and isolate for c sub 2, and you can see where the circumference of a circle, that formula, arises. The last thing we need to discuss in this lesson is Cavallari's principle. This principle says if the cross sections of two objects have the same area and the objects have the same height, then their volumes will be the same. If you look down below this picture, we have two stacks of coins. We have one uniform stack going straight up vertical, and then we have one that is curved. All right? What Cavallari's principle says, if we imagine each of these coins, one single coin over here and a single coin over here, they're going to have the same area. And if we had the same number of coins stacked up vertically in both of these stacks, as long as those areas of each one are the same, and as long as we have the same number of coins, the same height, the volumes, regardless of whether this is straight up and down or if this is curved, the volumes are going to be equal to each other. All right, that's Cavallari's principle, looking at cross sections of three-dimensional shapes.